First, just a little about me. I'm coming from a small company. It's called Elder Research, and we only have about maybe 70 employees across the East Coast, but we focus in data science consulting. And we work across a number of different industries, but as mentioned, the majority of my work has focused in the healthcare realm. Historically, a lot of my work has been on fraud, waste, and abuse, which this talk will cover. And more recently, my work has focused on mitigating the opioid crisis. So kickbacks, which I'll define in a moment, are estimated to make up roughly 20% of all medical fraud. And this means that there is a high incentive for us to be able to identify these without a reliance on hotline tips. But the problem is that investigating these cases takes a long time and they're very cost prohibitive. So as a result, we don't have a lot of known cases for us to model against. We're going to be reliant on unsupervised modeling techniques. And even if we did have a subset of cases that had been investigated, we would have had to have relied on semi-supervised modeling for the reason of a lack of investigation does not mean a lack of criminality. So what is a kickback? A kickback is basically, it's like a bribe. It's when something of value is being offered in return for a favorable action. I scratch your back, you scratch my back. The way this is going to look in healthcare is referrals. A physician sends you to another physician, or they're going to prescribe the use of a specific drug or equipment. And this is going to be an abnormally strong connection because in healthcare, there's supposed to be the idea of patient choice. The patient has the option to go to the physician that they choose. They have the option to use their choice of medication or treatment. So we're going to see that strong overlap in patients between two physicians or between a physician and a drug. And because we're looking for these strong connections, this lends us perfectly towards network analysis. So network analysis or graph analysis, it's really aiming to understand the relationships between different entities. So you're going to start with your nodes, which in this case we're going to define to be doctors. We could choose to have this be a multi-node problem where these would be doctors and or drugs, but we're going to focus on the referral aspect of the kickback problem, so we're going to stick with a single node problem where they are just physicians. We then need to connect these. And in this case, we're going to connect them based on their shared patients that they have in common. But recall that we want only the really strong connections. So we need to find a way that we can define a weight of these edges. Well, how are we going to do that? We could be real simple and just count the number of patients you have in common. But that's not going to work. If this means then that the physicians that have a high volume of patients are automatically going to outweigh the physicians that have a small number of patients, regardless of how strong that number of patients is relative to their own population. So we could look at a percentage, but a percentage is now going to give us a problem of creating a directed graph. The proportion of patients I share with you is different than the proportion of your patients you share with me. And that makes for just a messy problem. So we want to try to find something that is going to result in a single edge weight between each node. And that's where the Jacquard index comes in. So the Jacquard is really just the intersect over the union. It is a measure of shared information. And so if we had been looking at percentages, we would have looked at the purple over the blue or the purple over the red. But in the case of the Jacquard, we're going to look at the purple relative to the whole space, the gray here. So the Jacquard is simply the purple over the gray plus the purple. It could be just the gray if you're pretending that the purple is just highlighted. Now that we have our graph, how are we going to set up analyzing this to detect these kickback schemes? Most graph measures are going to focus on the flow of information. So measures of betweenness, closeness, those are all concentrating on the flow of information. If you're looking at community detection, which is common for detecting fraud rings, you're then focusing on the word of mouth idea of crime. I had this idea, I tell you, you tell someone else. But that's not the case for kickbacks. In kickbacks, it's a direct transaction. I do business with you, and I don't care who you do business with because I'm not doing business with them. So we need to find a way that can emphasize those direct connections. So if we're going to focus on this guy here in yellow, we want those direct connections, which are here in green. We wouldn't care about the connections that are on the far left. And what about these remaining blue edges? Do we want to keep them? Do we want to throw them out? Remember that we use the Jacquard measure to define our edges. So we're looking for what patients they have in common. Because of this, if I'm sharing the same set of patients with the same other physicians, it's mathematically necessary that they will be connected to each other. So therefore, having these additional edges is going to be of value to us because they provide that supplemental information. So that leaves us with an Egonet. So an Egonet is defined with an ego, which is this node at the center, and all of their first degree connected nodes, which are known as the alters, and all resulting edges between them. And we're only going to want to focus on these strong edges. We don't want the weak ones in the Egonet. Because if a fraudster is being smart, they're going to do the majority of their business by the book, and only a small proportion of it is going to be illicit. It's going to be a very lucrative portion, but it's small in their overall volume. So we're going to want to find a greedy algorithm that is going to slowly take the strongest nodes and add them piece by piece until we've hit a breaking point. And once we hit that breaking point, we're going to stop adding. So this is going to be, think of it a lot like the adjusted R-squared that is used in regression analysis. We want to be able to maximize the edge weight while minimizing the number of nodes we have included. So here is a simplified version of this formula. And we're going to iterate through each node in an Egonet until we hit the point of diminishing returns. At what point is the node that we add not worth the information that it is gaining us? So each node has its own weight. I know previously we talked about an edge having a weight. In this case, we're defining the weight of a node as a function of their edges. So if they're only connected to the ego, then that's just going to be their Jacquard edge weight. But if they have other connections to other alters, we're going to allow that to boost the overall weight because they do have that extra information. And this is of each node that we're adding, we're calculating the weight. And then what is the average weight of the nodes that we have included thus far in the subgraph? And recall that we're trying to find a breaking point. At what point is the amount of information we add insufficient? So we need to calculate what this difference of information is. So what was the average weight from the prior step compared to the weight at the current step? And we want this to scale. We want to punish having a large number of nodes. So in this case, we add this multiplier, where it's the number of alter nodes that are in the graph that we have used thus far, divided by the maximum possible number of edges in that Egonet. Now this value P can be used as a tuning parameter. If you want to be very strict in what you choose to keep, then you can do a transform on this, such as a log or a square root. If you want to be lenient on it, you can choose to leave it as is. So in a practical example, here was one graph that we had in our data set. This is, as you can see, incredibly messy. It is 153 different nodes with roughly 8,000 edges in between them for assessing just a single physician. But these dark edges here are what was selected by this algorithm. And this results in a graph that is much easier for us to analyze. We've picked out who are the key players that we think are the problem in this graph, in this network. You'll also notice that this is a complete graph, also called a click or a fully connected graph. This is going to happen very often because we allowed for the boosting of a node's weight based on their connections with the other alters. So now that we have this algorithm, how is it really performing? Well, our original graph that we were working with had about 6,000 nodes with 600,000 edges. It's a highly connected graph. They all connect to each other. There's no islands floating off on their own. And the median degree of each ego was 60. But when we run through the algorithm, we were able to reduce our edge count to 1% by having only 6,000 edges left. Recall that this is an iteration. We slowly add each nth node. So every node is guaranteed to have one connection, and the testing starts with the addition of the second alter. 93% of ours stopped after the first node. And this is what we would expect because we are looking for, in healthcare, we should not be seeing a large number of physicians that have strong connections to others. That's supposed to be a rare event. And how does this perform in terms of computation? Graphs are known to be very cumbersome. They're known to require special techniques, special software. This was run just using tabular data of an edge list, simply put into a for loop. So as long as you have the means to handle the size of your edge list, nothing else special is required. You don't need multiprocessing. You don't need something like Neo4j to handle your graphs. You don't need something intense like a GPU to handle everything. And even with all of this, we were able to run this algorithm in about 2 minutes. And that's with how strict we chose to be with our method. If you choose to be more lenient, it's going to have to iterate through more times. But even with that, our worst case was roughly about 20 minutes. And the way it's doing this is it's analyzing the addition of the nth node to every Egonet at the same time. So that's what allowed us to get these good runtime results. So now that we have these results, how are we going to interpret them and deliver them to the investigators? So each subgraph now has this score that we have defined. And with that, they can be ranked. And so with this distribution, you can see there's only a few of them that are up close to 1 with their final subgraph score. This is to be expected because, again, the nature of our data is that there should not be a large number of physicians that have strong connections to others. So once we have this ranked list, we can deliver it to the investigators. They can prioritize their caseload and become more efficient. Also, when we're providing this ranked list, we should try and remove any perfect subgraphs. So remember that we're going to have a lot of graphs that look like this, perfect clicks. Well, in this case, there are 7 nodes, but they're all the same graph. We don't want to have to point to this graph 7 times. That's going to fatigue the investigator. They're not going to find it very interesting. So we need to be able to only highlight the strongest node, and we're going to truncate the weaker nodes from this list. This isn't going to be a problem because all the nodes will still be investigated because ultimately the graph is what's being investigated. It's just what point do we highlight out of this graph. When we applied this, we were able to remove about 27% of the egos that we were analyzing. So thus we removed about 2,000 different nodes. And lastly, we can pair this with supplemental information, such as the number of patients or the amount of dollars that are involved in this. Because recall that we used the Jacquard, this put everything on the same scale. Physicians who had a large number of patients were treated the same as physicians who had a few number of patients. You can now bring that information back in and weight them with information such as this. And by doing that, you'll be able to then create a new metric that'll allow you to highlight those that are high in dollars and high in their subgraph strength. So in conclusion, we were able to set up a graph And by doing this, we defined our nodes as the physicians. We connected the edges based on the patients that they shared in common, and we defined the weight of those edges based on the Jacquard value for that. We chose to focus on the Egonet for each physician independently without crossing that information. And we applied this algorithm in order to select an Egonet subgraph that had the strongest relative edges. And then, because each subgraph now has a score, we can rank them for investigation based on that score. And this ranking has allowed for the prioritization of cases, maximization of efficiency, and eliminates the reliance for hotline tips. Just a fun summary note, having looked at our top 10 that were created from this list, about 7 of them are actively under investigation. We have gotten good feedback with this metric. At this point, I can take any questions.